Are doing well. My name is Shriya Bansal and I'm currently working as a software engineer at Microsoft. And now in this video, we are going to move ahead and talk about different strategies which can help to handle deadlocks. So far, we've already talked a lot about what a deadlock is, what's the difference between a deadlock and a starvation, how do we understand a deadlock, right? And what are resource allocation graphs. Now, since we have so much context around deadlocks already, now would be a good time to introduce the concept of how do we handle deadlocks, which is pretty much why this topic was introduced. So first of all, we'll talk about the four strategies in a brief manner, and then we'll take all of them in detail. First, let's actually talk about the fourth approach itself, which is known as the ostrich approach or ignoring the deadlock approach. In this approach, if a deadlock is there, simply ignore the deadlock. Okay. According to this method, right, it is simply assumed, right, that a deadlock would never occur. In this kind of an approach, you just assume that a deadlock would never happen, right? This approach is usually used by many operating systems where they assume that a deadlock will never occur, which means that if a deadlock will happen, they will just simply ignore the deadlock. This kind of an approach is actually very beneficial for those systems that are only used for browsing purposes and for very simple tasks, in which anyway the probability of a deadlock is very simple. Okay, thus ignoring the deadlock might be a solution altogether and useful in many cases also, right? But it is not perfect. Okay, it's a good approach if you have normal like I would say use cases, but it's not the perfect approach in order to remove the deadlock from the system. Okay, and this approach is kind of like a trade-off, okay, between the correctness and the performance. Okay, for example, the operating system like Windows and Linux mainly focus on performance. Okay, however, the performance of a system decreases if it uses deadlocks, okay, handling mechanism all the time. If you're just constantly using mechanism deadlock all the time, even if the deadlock happens 1 out of 100 times, right, then it is actually completely unnecessary to use those procedures altogether. If in 100 situations a deadlock is happening one time, you can actually ignore that deadlock altogether by just simply restarting the system. Okay, that's what the overall idea about deadlock ignorance is. Okay, then we'll come back to the idea of deadlock prevention. Okay, so what happens in deadlock prevention is that we actually prevent a deadlock by doing the resource scheduling, okay, in such a way, in such an optimized way, so actually to negate at least one of the four conditions. Idea is very simple. You have four conditions, and if all four of them are completely true, that means a deadlock is occurred. So what happens in the deadlock prevention technique is we simply try and avoid to have all of these conditions together. We'll try that at least one of those conditions are untrue, which is necessary for a deadlock to not happen. Okay, so we have 40 conditions. We'll just try that at least one of them is not happening, and thus a deadlock is preventing. Okay, because we know a deadlock only happens when there is mutual exclusion, hold and wait, no preemption, or circular wait. Okay, and if all of them are happening simultaneously, even if one of the conditions are violated, right, at any point of time, the deadlock would never happen. And that's what pretty much the idea is, that we just have to fail one of the four conditions. Okay, but there can be like other conditions which are happening, right, but we just want to avoid one of these conditions. That's what the idea about deadlock prevention is. This is how you prevent a deadlock from happening. The second one over here is deadlock avoidance. What do we do in deadlock avoidance is that we avoid deadlock by careful resource scheduling. Okay, so what happens is the operating system checks whether a system is in a safe state or is in an unsafe state. Okay, so if any time when you have multiple processes, a system is always in a safe state or in an unsafe state. A safe state is, that means a deadlock is currently not happening, or an unsafe state is that a deadlock may or may not happen, okay, whenever we perform some steps in the operating system. Okay, now this kind of a process continues, right, until the system is in safe state. Okay, and once the system, so if you have system in the safe state, then it's fine. But the moment the system moves to an unsafe state, the operating system basically takes a back step. Okay, so what do is, you have the entire system of all processes, you start allocating the processes and the resources. You have a process, you allocate resource to that process, and you check whether the system is in a safe state or is in an unsafe state. Let's say the process is in a safe state. Okay, then you move ahead, take the next process and allocate the resource to it. Then you check again if the system is in a safe state or is it in an unsafe state. If it's in a safe state, then just move ahead. Let's say now the process P3 and the resource R3 is get allocating to it. Now the moment you did that, the system went into a safe state to an unsafe state. An unsafe state is the one in which a deadlock may happen. So the moment you even come to an unsafe state where there is even a probability for a deadlock to happen, you simply backtrack. Okay, and that's what I said. You continue allocating the resources, you continue allocating the processes, the resources until the system is in a safe state. And the moment the system moves in an unsafe state, you simply backtrack. That's what careful resource scheduling is. In other words, we can say that the operating system basically reviews each and every allocation so that it doesn't cause a deadlock in the system. Okay, and the third one is deadlock detection and recovery. Okay, so in this situation, what happens is the deadlock has actually gone into a deadlock situation. Okay, now in this process, let the processes actually go into the deadlock situation, right? And then it basically periodically checks whether deadlock has happened in the system or not. So first part is to detect deadlock. Okay, so there is like a process, there is like a mechanism which we will talk about later, which is constantly going to check after every period of time or after every few dedicated period of time whether a deadlock is detected or not. Okay, and if it is actually detected, right, then there are some sort of recovery steps that can be taken in order to make sure that the deadlock we come out of the deadlock. Okay, so a total of 4 strategies that we have introduced over here. First is deadlock prevention, that we actually prevent the deadlock from happening by negating or by making sure that any of the 4 necessary conditions of deadlock actually fails. The second way is deadlock avoidance, that whenever we do the resource allocation, we do it in a very careful way, and every time we check whether the system is in a safe state or not. Even with a single allocation of resources, if it takes the system to an unsafe state, we simply backtrack and roll back that resource allocation. The third step is deadlock detection and recovery, where we are not doing any prevention here, we are not doing any avoidance over here. In this step, we just constantly check after some time whether a deadlock has happened or not. And based on that, if it has happened, we just recover and take some recovery steps. The last part is the ostrich approach, or we also know it as the deadlock ignorance, wherein we just ignore the deadlock even if it is present. In this approach, there's hardly an instance where a deadlock can happen, and even if it does happen, we just simply restart the system and do not apply any deadlock recovery mechanisms. All right, so this is what a very high level overview is about all these strategies that exist for handling deadlocks. Now what we are going to do is we are going to go in detail and talk about all of them in a slightly more enhanced format. Okay, now a deadlock can actually be prevented if we already know all the 4 conditions, right? And we are now going to talk about deadlock prevention. Okay, what did we used to do in deadlock prevention? The deadlock prevention technique said that just make sure that any of these 4 conditions fail and you're good to go. Okay, so what happens is we know all the 4 conditions: mutual exclusion, hold and wait, no preemption, and circular wait. And we've already talked about them in detail also in the previous video. Okay, so if we actually simulate a deadlock, okay, let's say deadlock is a table, okay, which is standing on 4 legs. This is just a hypothetical example. Assume a deadlock is a table which is standing on 4 legs, right? Then we can also simulate those 4 legs as these 4 conditions. Okay, table, the overlying tabletop is the deadlock, and the 4 legs of the legs can be 4 legs of the deadlock or the table can be thought of as these 4 conditions. Even if one of these conditions fails, the tabletop will not be able to stand. If we break even one of these legs of the table will fall definitely. Okay. The same happens with deadlock. Even if you violate one of the four necessary conditions and don't let them happen together, then we can actually prevent a deadlock. Okay. And these are all the four conditions for that. Okay. Which we just